Okay, we're back, and basically last time we were talking about self-inductance, and now we talk about mutual inductance. And mutual inductance is the basis of the transformer. It's basically, I can create one coil to create a varying magnetic flux, and I can feed that varying magnetic flux to a second coil, which is then bathed inside this varying magnetic flux, and it creates a back EMF. So, now, all right, so what? But what this means is that I can have an EMF which is varying for this first coil, and that creates an EMF which is varying for the second coil. And they are physically connected by magnetic flux, not wires. So I can have this kind of really cool thing where actually they can be separated by glass or plastic. So I can have a non-contact way of getting AC energy from one circuit to another. And so if you have a cordless toothbrush, if you have an electric toothbrush that just sits on the little base, on that base there's a coil of wire which is basically been driven by AC. And in the handle of the cordless toothbrush there's another coil of wire, the secondary, which is receiving that changing magnetic flux and saying, I'm creating an EMF, and you can use that to charge a little battery up. So you can have, contactless transmission of electrical energy, which is kind of cool. And that's one thing. And then the second thing is I can start playing games. I can start playing games with the number of turns. And I can have a primary, which only has a few turns, and a secondary, which has a lot of turns. Or I can have a primary which has a lot of turns and a secondary which has a few turns. What that then does is a really amazing thing, which is I can trade off, say, for example, high voltage, low current power in the primary for low voltage, high current power in the secondary. There'll be some energy loss because of heating effects, but not much. So in principle, power here equals the power there. And I can play games. So whereas with DC, if I want to change voltage, I can. I typically do it using, circuits which contain resistors, and there's heating effect in resistors, and it's, I don't get much for it. With AC, I can basically take AC generated, as long as it is alternating, I can step up the voltage and go very high voltage, very low current, which means it's very little energy loss. I can then ship it across the country, 50 miles. And then when it gets to the little town that I want to distribute the energy to, I can have another transformer which goes from high voltage, low current to low voltage, high current. I share that current out with all the houses. So it's an amazing system. And that's the magic of AC. That's kind of why AC won out over DC. It's just very adaptable, all through this. So what do we learn about it? We say, well, when magnetic flux through one circuit loop varies because of a time-varying current, you've got to have an alternating system. In a nearby circuit element, we call this mutual inductance. So this is two circuits, maybe two coils, two circuits side by side. Consider two closely wound coils of wire. Coil 1 has N1 turns and current of I amps, and it creates a magnetic field that varies. It passes through the second coil, and we can see that there's a mutual inductance. So the inductance in the second is N2 phi 2 over I1. We can play the game. I don't do much with this, frankly. You don't even have to know that equation. You want to know the outcome, okay? If we continue, we can say, all right, EMF caused by a mutual inductor, and we say, well, if M2 is that, I can go yada, 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 and I come down here and I go, the inductance in 1 is equal to the inductance in 2, so the EMF in 1 and the EMF in 2 are given by these. And what we see is basically, well, again, don't worry about that. Worry about where we're going with it. And we're going to be going towards transformers primarily, okay? So what do I want you to get out of that? I want you to know about self-inductance, and then I want you to know there's this thing called mutual inductance, which is the basis of the transformer. Okay, let's talk a little bit about the inductor being one type of device and the capacitor being the other type of device. And so I've got a circuit. It's an impossible circuit to really make. All circuits have resistance, so really I should have a little bit of resistance in here. But it turns out that from a discussion point of view, sometimes, resistance is like friction. And sometimes we do a lot of physics without friction because it makes life simpler. We're doing the same thing here. We're not going to worry about resistance to begin with. And what I want to try and get across to you is the fact that a capacitor with an inductor is like a mass on a spring. Mechanically, it's a mass on a spring. And we've been here before. So imagine, let's just recall, so we have a mass, we have a frictionless table and we have a spring with a mass on it, and we move the mass to one side, and there's a natural frequency for this spring mass system, and so it oscillates backwards and forwards as time passes. It works. We've done the math of it. We've played with it. So what's going on here? I'm going to try and convince you that this is the same, analogous physics. Assume the capacitor is fully charged. Clearly, if there's no charge on the capacitor and there's no current flowing through the inductor, there's nothing happening. So we've got to prime this thing. Just like when you put a mass on a spring and you just leave it on the table and you look at it, nothing happens. You've got to put some energy in it to get it to start oscillating. So we've got to put some energy into this system to get it to start oscillating. So we've got to charge the capacitor. That's the obvious thing to do. So we charge the capacitor. And then we say, okay, you charged, let it go. Let whatever needs to go happen. So we say, assume the capacitor is fully charged. So initially all the energy is stored in the capacitor. When the switch is closed, I don't show a switch on here, but there's a switch on here somewhere. When the switch is closed, the capacitor discharges through the circuit, which means through the inductor. And a current flows through the inductor. Not just a current, but a changing current, because the capacitor discharges non-linearly. So, okay, so a changing current passes through the inductor. A current flows through the inductor. The current reaches a maximum as the capacitor becomes completely discharged. At this point, no energy is stored in the capacitor, and all the energy is stored in the inductor. You got. Remember that term for energy in the inductor depends upon current flow. The flow continues at a slower and slower rate as the capacitor becomes discharged with the opposite polarity. Eventually, the capacitor is fully charged in the opposite polarity. Current flow around the circuit is zero. At this point, all the energy is stored in the capacitor again, and the oscillation continues. So basically, you start off and you have an electric field, and then you get the current flow, so you get a magnetic field, and then you get an electric field going the other way, and then a magnetic field the other way, and then an electric field the other way. So I charge, I discharge, I discharge, I charge the opposite way, I discharge, I charge the opposite way. That's the capacitor going backwards and forwards. Having energy, having no energy, having energy, having no energy, having energy. And for the magnetic component, I create a magnetic field, so I've got the energy, and then I've got no magnetic field, then I have the magnetic field, I have no magnetic field, then I have the magnetic field, I have no magnetic field. So just like this thing goes from spring potential to kinetic, to spring potential, kinetic, spring potential with the opposite sense on the polarities, on the directions, this thing's doing the same thing. You're swapping backwards. It's like you're taking the electrical energy, electromagnetic energy, and you're swapping it from electrostatic to magnetic to electrostatic to magnetic. And at any point, you've got the total amount of energy is the same. So it's a very analogous system, which means that we can use the math of it. So we say the total energy in an LC circuit is constant, so a half Li squared plus a half Q squared over C is my total energy, so it's a half Li squared plus a half Q squared over C. Isn't that the same thing? Looks like the same thing to me. This theoretical circuit has no resistance, so no energy is lost to heat. Resistance is like friction. So the total energy is constant. We've got no energy loss due to resistance heating. So let's do some math. du by dt equals d by dt of what we just had. Take out our L and take out a 2. So d by dt of, and let's call this I squared I dot I, or I times I. No, it's not a dot product, it's I times I. Plus 1 over 2c d by dt q times q. And oh, I know where we're going. So this is L over 2I di by dt plus di by dt times I plus, we're breaking this up, yada yada. Again, you don't have to repeat this. So u by dt equals 2L over 2I di by dt plus 2 over 2c q dq by dt, which gives us Li di by dt plus q over c dq by dt. And if we remember that the total energy doesn't change, so du by dt equals 0. And if you remember that I equals dq by dt, and therefore, and also that di by dt equals d2q by dt squared, then we substitute that in and we get du by dt equals Li d2q by dt squared plus q over c times I. Dividing by I gives us L dq d2q by dt squared plus q over c. So now we've got a quadratic a differential equation in terms of q. And we say rearranging gives us d2q by dt squared equals minus q over lc, which equals minus L1 over lc times q. And then we say, oh, d2q by dt squared equals minus 1 over lc times q. Looks like d2x by dt squared equals minus k over m times x. And that equals minus omega squared x. We did that in mechanics. So for mass on a spring system, omega equaled root k over m, and the solution was x equals a cosine omega t. Plus this was a phase constant. Yeah, this was if you didn't start off right. By analogy, for an RC circuit, we get that q equals q max cosine omega t, so there's kind of like that. And omega equals 1 over, square root of 1 over LC. And by differentiation. So
we should just memorize the last formula?
you should know, you already know that, so you should remember that, and you already know that, so you should remember that. And I don't particularly care about that. It's just a differential, isn't it? You're just differentiating that to that.
So the result is...
I mean, so yeah, you should know how to do it. But the important thing is the analogy, isn't it? It's, oh yeah, omega equals square root of k over m. Well, this is omega is equal to square root of 1 over LC. And we had x equals a cos omega t. Well, q is equal to q max cos omega t. So learn those two analogies. So now, frankly, if you sat me down in a room with a piece of paper, I couldn't repeat that in any decent length of time. And you don't have to repeat that in any decent length of time. If I'm the kind of person where I like to check things out, so you might want to spend some time and just go over it, but you know, it's not going to be, you're ever going to be tested on it. Certainly not in this course. But get yourself comfortable with this analogy. You know, the more comfortable you are with the analogy, the more you can visualize the mechanical system and infer things that will apply to the electrical system. So that's what the name of the game is. That's why they're doing it. And then, yeah, to determine the phase angle, forget that. It doesn't matter. Okay. So let's just stop there and